actually not said too much about the way the electromagnetic waves are generated, and we are not going to be describing that in detail in the course. We are actually looking at things when we are far apart from the sources, and the waves are displacing on vacuum or different systems. So the wave model that we have just described, meaning describing the electromagnetic radiation as an electromagnetic wave with this a e to the I k minus kx minus omega t, it's a good model to describe the transport and how it goes around obstacles. Okay, but I can have a wall and see what the effect of that is, the absorption of the light in there, etc. That's one model where this system works well. There's another model which is a corpuscular model. This is a quantum model. That the name that or the feature that comes about is photons. Photons are electromagnetic excitations, quantum electromagnetic excitations of the fields. Okay, and they are relevant. You know, the initial models for describing light were really corpuscular, and people tried to measure them and did a lot of things to actually try to describe these corpuscles, describing the electromagnetic waves. But then came around Maxwell and said, look, you know, guys, you were all wrong about this. You know, electromagnetic waves are waves, and here I can prove it. And you know, and the model works fantastically. But then when you want to look at how the system, the energy contained in an electromagnetic wave is high enough to actually excite or ionize the atoms in a particular piece of material, the way to describe that is not through a wave model. The way to describe that is through the corpuscular model again. So now it would be better to think of something interacting very strongly with the material as a collision, and where the energy is absorbed, collected by an electron, and making a transition to a higher state. That kind of processes are better described by photons, not the wave model that I'm describing here. And then later in the course, we're going to get to this description in more details. And then there's the lighter part, the one that is really enjoyable about electromagnetic waves is ray optics, geometrical optics. You can understand, for example, how the optical lenses work without really getting into the details of if this thing is an electromagnetic wave or are there photons involved, because in this case, the only thing that is really important is that the obstacles that you are putting in front of the wave are very large compared to the wavelength of the obstacles. If the wavelength of the electromagnetic wave is comparable to the size of the objects, a phenomenon called diffraction will appear, and you are familiar with that from other fields, from fluids, for example. But that also happens in electromagnetic waves. So the geometrical optics, which is what we call ray optics, is good for the description of phenomena called refraction and reflection. And that is what I'm going to try to describe next. This is what the ray optics means. This is, for example, you can imagine, you know, being all by yourself in a huge pond with no waves on it, and you just throw a stone in the middle of the pond and start to look at the phenomena that happen. and you will see these circular rings that start to open and travel with the velocity of sound on the surface of the water, okay? And you can actually pinpoint the wavefront there, followed by a next one and a following one, which are the perturbation on the surface of the water. And here, for example, I have a point source in space that is producing a spherical sound wave that produces a high density in this area and a rarefication in between, okay? So, and you have this alternating patterns of rarefications and high intensity and high compression in air, okay? So you can define then or identify the different wavefronts in this case, and they all will have this circular geometry with respect to the origin, meaning the spherical, essentially, and this will be a front of the wave, and one can think of rays that describe the way the front will evolve in the future. Okay, so these rays are sort of like this. They sort of flow in this direction. Okay, and if it's pointing in that direction, it means that the front will be close to here in the next time. Okay, so this is what I'm depicting here. So the rays are usually perpendicular to the wavefronts. So they actually are telling you in which way the wavefront will move in the future. Okay, so we have this source, we have this wavefront, and we have all these rays that are perpendicular to the wavefronts. We can draw as many rays as we want. We just want to have an idea of how the things behave. We could, you know, if we draw too many, we will lose understanding. But this is sort of reasonable what it is. If you are very far apart from the source, this region over here will be flat. You wouldn't be able to see the spherical surface. Like I mentioned before, the radiation that gets to the Earth from the sun is essentially a plane wave, meaning it's something like this. You don't see the spherical aspect of it. It arrives simultaneously as a flat plane, and the rays in that case are perpendicular to these wavefronts. Okay, so this is sort of a qualitative aspect that is very reasonable to actually get some information, for example, as formation of images. Okay, and we're going to get to that later. Okay, let's see how does it works. Here we have an example of the type of phenomena that I would like, not shopping, by the way. Huh? The idea is that we are seeing two phenomena here. This lady is actually seeing her image reflected on the window, and she's actually also seeing this mannequin inside the window. Okay, so we have two things. One of this is the reflection. So there's light here outside. The lights illuminate her body. It reflects from her body, goes to the window, and comes back to her eye. So she sees the reflection. And we can also see it with the camera. Okay? But she can also look through the glass and see an object behind the glass. Okay, this happens because the glass is transparent, and actually, since it is transparent, the electromagnetic radiation, the light, can go in all over directions, and in particular, it can reflect back to her eye so she can see it. Okay, but before it does that, it has to pass through the glass. The passage of the light through the glass is what it's called refraction. The reflection is the phenomena that the light generated here in the jacket arrives to the glass and it's bounced back to the to her eyes. Okay, that's the two phenomena, reflection and refraction, and they both can be described qualitatively. I would say quantitatively, very accurately. These are all electromagnetic waves, and so we're going to use the model of optics and rays to actually understand the formation of images. Okay, because what is this? You know, this image that she's seeing here. You know, and we are also seeing it. Okay, where is it really? Okay, yeah, like Alice in the mirror and Wonderland. Okay, is there anything behind? There's something we have to understand about materials, is that the velocity of light inside a material, even though it is transparent, is different than the velocity of light in vacuum. Okay, and there's a way to quantify this difference by defining what we call the index of refraction. So if C is, this is 2.99 blah, 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 times 10 to the 8 meters per second. Okay, so this is the velocity of light. The velocity of light inside a piece of glass in general is less than the velocity of light. Okay, the velocity of light in vacuum is essentially the maximum velocity of anything. Okay, of any physical object, not a phase. A phase can go faster than this, but the velocity of light in vacuum is this is the maximum velocity of any object. Okay, the velocity inside the material, the wave front inside the material will travel at a speed that is a little bit less than this. In general, n is greater than 1. Regular glass in the windows of your house, it has an n equals approximately 1.4. And that has implications about image formations and whatnot. And we are going to deal a bit with that. Okay, so we have two types of reflections in materials. One of them is the one that I'm showing here as a specular reflection. For specular reflection to happen, that is the one that you get when you look at yourself in a polished metal. You really need a very sort of smooth surface where the actual rays come in and bounce back, okay? And a ray that arrives here essentially bounce back the same way that a ray that arrives there, because this is absolutely flat. If the surface is not flat, what we get is a diffuse reflection. Okay, this is easy to understand in terms of the physics, because whatever happens here is the same as it happens here, but almost everything we see is reflecting like this way. You know, all the objects we are actually seeing at this very moment we are able to make an image of them because they essentially reflect light mostly in diffuse ways, okay, like this. So we can see the textures of the objects in close to us, and this has to do with diffuse reflection. This kind of specular reflection is the one that you get in a mirror. A mirror is essentially a very polished metal. The one that is in the bathroom in your house probably it's also a polished metal. It's in a glass, but it's painted with some sort of silver containing material, actually, very narrow layer. And that makes it look very polished, and actually doesn't oxidize with time because it's behind the glass, and you're seeing it through the glass. Okay, so that's what makes the specular reflection so good, and it lasts so long. Okay, The first mirrors that were inverted were simply polished metals, and somebody discovered that very early in time. Okay. Now we also have when an incident radiation is incident, when a radiation is incident in transparent material, there are two actually phenomena happening. Part of the incident energy is actually radiated back to wherever the source was, and the other one is transmitted. So we have a part of the energy is reflected and part of the energy is refracted. If you are standing with this lady, for example, that we had in this example, of the light that is incident on the surface of the glass, almost 96% of the intensity of light incident on the surface make it through the glass, okay? And only about 4% of it is reflected back, okay? So the image is actually being made essentially by about 4% of the total energy that is coming out of her body going into the window. I'm saying out of her body, meaning out of her shape, essentially, because it's external light that's illuminating her. And the light, almost all of them go through, 96%, but only 4% reflects back, okay? We're gonna see that in a moment. Well, I don't know if in a moment, probably in the next class, okay? This is a very sort of relevant aspect also, is that the laws of reflection and refraction, these are empirical laws, but these laws can be proven from electromagnetism, but I'm not going to do that here at this very moment. If I don't know if I'm going to be able to actually show you that, but there's a section in the book that actually deals with this aspect. It's worth reading, but it's, you know, at this point, I want you to understand the laws, not really the origin of it, okay? So incident, reflected, and refracted rays and surface normal are all contained in the same plane. And that plane is called the planes of incidence, okay? So essentially, this is a surface. I'm cutting the surface here. So I have here material A, here material B. And now I'm drawing this incident ray. This plane, the blue plane here, is in the same plane as the incident ray. This incident ray is in this plane. It's called the plane of incidence. It is also the same plane where the normal of the surface is contained, and the reflected ray is also in the same plane, and the same is true for the refracted plane, okay? So all this line, and this line are on the same plane, okay? That means the second law of reflection and refraction is that the angle of reflection is equal to the angle of incidence, okay? So this would be the angle of incidence, theta A. I use theta I here and theta R, but okay. Theta A, and we should use this as theta A prime, essentially, to actually indicate that they are both contained in material A, okay? So this is the angle of incidence, and this is the angle of reflection. And what happens is that if this is a surface normal, and the angles of reflection and refraction are measured with respect to the surface normal, they are both the same. This angle, or this theta A, is equal to this theta R. So this is the second law here, okay? And the third one is Snell law, which means that if these two materials, the material A and material B, they are different. So essentially the refraction index in this case is different from here. That's what makes it a different material. Okay, so there is a discontinuity in the refraction index from going from material A to material B. Okay, and so what happens then? The law that actually regulates this is that NA sine of theta A is equal to NB sine of theta B. By looking at this graph, can you actually tell which one of the index of refraction is higher? Anybody? I should try to make prices, you know, to have an answer here. Essentially, if look at this side, so if theta B is smaller, so this is a fixed value, okay? And let's look at what happens in this side. So if theta B is smaller than theta A, that's what's going on here in this angle, it means that NB has to be larger just to make this, to fulfill this equation. So whenever you have a discontinuity in the index of refraction, the incident ray, what it does, it gets closer to the normal of the surface. That's a general rule. If you come here and this is index of refraction is higher, it goes very close to the normal. Okay, and also I have drawn a second set of arrows pointing in a different direction, pointing in the opposite direction, which means that this is completely reversible. So if a ray goes like this, if I put the source in here, it will go like that. Okay, so that's interesting because you know, if you have an eye and you're looking through here, you know, let's draw an eye. How do I do this? Can I do this? I don't know. I don't think I can. No. Going to access. No, that's why I need the other thing. Well, I can draw an eye here. And if you look at this object, you will feel that the object is actually located around here instead of here. Okay, that will be the image that you will get. And this is what happens when you are actually seeing a fish inside the water. Okay, because the water has an index of refraction. What did I do? Oops. Now I lost my okay, spotlight. Here we go. So the water has an index of refraction that is likely higher than air. Obviously, air is almost nearly equal to vacuum. So by definition, it has index of refraction 1. And this water is probably 1.2 or 1.3 or something like that. Or there's a table somewhere. So it means that if you're seeing a fish under the water and you believe it's here because that's the way your brain interprets that you see the light there, the actual position is over here. Okay. So whenever you try to shoot the fish and get it by hitting it there, you will never do that because the fish is in a completely different position. And something you shoot outside doesn't follow the angle of reflection and refraction when it gets to the surface. Only the electromagnetic wave does. Okay, that's good for the fish. That's why I'm vegan. You know. Okay, next. Okay, so this is the general thing. So a ray entering a material with a larger index of refraction refracts, bends toward the normal. That's what happens. Okay, this is material A. This is higher and B is higher than A. This is what happens when when the thing is going away, it's the opposite, meaning this is exactly the reverse as that one. That's my first picture. So when you're going to an index of refraction that is smaller, the thing moves away from the normal. Okay. And when the thing is actually oriented normal, it doesn't really matter. It doesn't go anywhere because theta A and theta B are both zero, so there's no influence whatsoever if the incidence is normal to the surface. Okay. This also is true in terms of Snell's law. It's also valid because both angles are equal to zero. Okay, this is what I was explaining to you before. This is not supposed to be a bent ruler. It's supposed to be a ruler, but there's a surface of water there if you can actually see it. And well, you must have had this experience many times, even when you look at yourself standing on the bottom of a pool and you actually see your feet a lot closer than what you think you are. Essentially, you look shorter by looking yourself standing on the pool. Okay, and this is the idea of what's going on here. So this is the extreme of the ruler. Okay, and the extreme of the ruler gives the idea that two rays coming from this point are supposed to get into your eye, and your eye, what will do is refocus on them on the retina. You need the two things, the two rays, to actually give you the idea of depth in your eye. So you get this ray and you get the other ray. They are wide apart here just to make them visible. And this is what actually happens to them when you have the ruler inside the water. Okay, they come like that and come like that. And what do you interpret of them? You interpret that these two things come from a point around there. So that's why you see, you think that the ruler is bent. It's sort of like that, and it's sort of bent up. That is what looks up here. Okay, that's what the picture is recognizing. So this is a position, and this is where your brain thinks the extreme of the ruler is. Okay. There's another very important feature of what I'm doing here is I'm actually telling you that if you in order to get an image of a point, you have to intersect two rays coming from the same point. Essentially, the image of this point will mean that a ray coming from here very close by. Remember, the rays are essentially showing you the position of the wavefronts. Okay, and so you can always draw two rays very close by to each other, and what the eye does, it's almost like a lens. It focuses the light on the retina to make an image there. The retina is the sensible part of the eye. But what you need for that is that two rays coming from this point should intersect finally in the retina. And that gives rise to an image, the intersection of two rays. And that is something very sort of, here is the index of water refraction, 1.33, not 1.2, as I told you before. Okay. So that's a key part of forming images. Okay. Now back to the wave part of it. So you should be reminded that for waves in vacuum, how are we doing in time?
We seem to have like 7 minutes left.
7 minutes left. Okay. I think we're going to be able to make it. Let's be reminded that for waves in vacuum, the wavelength is equal to c times t. T is the frequency of the light. The frequency of the light is something that is really fixed by the source. Okay, it's not something I can change. But the wavelength can change. Why? because the frequency is fixed by the software. T is 1 over f. Okay, so if in vacuum the wavelength is c over f, inside a material the wavelength is changing. It's actually v over f. It's the same expression, but now the velocity of light have changed. So the wavelength in general inside a material is smaller than the wavelength outside, because n is in general, not in general, n is always greater than 1. Okay. Another concept, total internal reflection. Okay, this is also look at this is the experimental thing here. Okay, so we have what are the objects? We have a very intense parallel light coming down here, and here we have 3 mirrors, one there, there, and there, that reflects the beam in 3 different directions. Okay, the first 2 can the lights come in, the ray is reflected to the surface, part of it is refracted from the surface, and part of it is reflected. You don't quite see it here, okay, but here you can. Okay, so and for this ray over here, you can see some of it is reflected, and you can see the spots actually here. These are the spots of the reflection. Okay, these are very light, and this one is very strong. And what happened with this one? There's no light that goes out. Okay, and how do we explain that? Well, this is Snell law has to be valid every time, so it's valid here. So, but this media here, or material, this material here is air, and this material here is water. So the actual this thing has a higher index of refraction than this one. So there is an angle, and let me go to the next expression here. There's an angle here. So this is theta b in the second material. Theta b is in the second material. This one over here, this is b, this is a. Okay, so sine theta b, this can be 1 at one point. Okay, because in NB, this thing is greater than 1. So there could be an angle here that will make this thing equal to 1. So if this thing is equal to 1, theta b will be equal to 90 degrees. Okay, and that will happen for theta a equals to theta critical. Okay, so what is the phenomenon that we are seeing here? That's the phenomenon we are seeing here. If the light gets into a thing like this and gets totally internally reflected, you don't even have to put anything metallic in here. Simply the difference in the index of refraction. Okay, so let me answer this. Okay. So this has really important applications, and one of the important one is the it has a medical application, doing endoscopy. Okay, that is exactly what happens. One of them is doing endoscopy, and the other one is, in my case, is actually driving the fiber optics that brings the electromagnetic signal. Wait a second, guys. Be back in a second. Sorry, guys, I'm back. Okay. So fiber optics, it's a technological thing, and there's something to be learned about this. Okay. Boom. The other phenomena that is really important is dispersion. Okay, the index of refraction can be a function of the wavelength, and if it changes with the wavelength, it means that when you have light going through a media, the angle of refraction will be different depending on the wavelength. And if something like that happens, you can actually separate the colors of light. Okay, and there's a prism there. You know, that what is not listed here is also diamond. Diamond has an interesting property that you could see that, and so you can see sort of a rainbow coming out of a diamond, simply because it has this very high index of refraction, and the index of refraction is strongly dependent on the wavelength. Okay, so that's an important thing. The other important thing, and with this view graph I stop, is that the concept of polarization, which I have already mentioned, and we can manage polarization or do some engineering with polarization in electromagnetic waves. This here, for example, are transverse polarized vibrations on a string. So it's a wave on a string. So you can actually, it's a guitar, and you can actually produce a perturbation like that, or you can produce a perturbation in the direction perpendicular to that, or you can actually do a combination of both. And a combination of those will give you a circularly polarized vibration. And you can have something like a slot like this that could make a selection of the polarization of the waves that you have. So we're going to get into details about this in our next lecture. This is back to the wave things, okay? So polarization of the light is something that is very important, and this is that you know, has a lot of applications. One of them is polarized sunglasses, and I'm going to try to get one for you for next session, or if you can, try to get a polarized glass, because I have a few experiments that I would like you guys to do, and we can do it together actually. Okay, so I guess it's been, you know, this is it, you know, I'm almost all of it, all of the time it's been spent. I don't know if there's any question at this time. So we're all clear? I don't know if
yes.
you... Okay, okay. Please feel free to stop me, okay? I'm not in, you know, I'm always in a hurry to actually cover as much topics that I'm supposed to cover, but that's my pressure. Your pressure should be to understand. So if there's something that is not clear enough, I could, you know, go into the details, go back and try to explain it better. You know, I certainly can do the job. If sometimes what does is assume that people knows a few things, but that is a mistake. One should assume that somebody knows nothing before explain, but it's very difficult to actually take that into account every time. Okay, so my apologies if I'm not very clear on these things, but you know, you should try to get me to explain them. Okay. Okay, guys, this is it. Have a nice weekend, and let's take it from here. Okay.
All right. Thank you very much. Take care, teacher.
Ciao, ciao.
Professor, take care.
Ciao.